So here's where we were. We were imagining we've got a system of two spin 1/2 particles. You can also use this formalism to describe combining spin angular momentum and orbital angular momentum, but here we're just imagining it's two separate particles. So it could be like the proton and the electron in a hydrogen atom. So we've got two particles together. And one way to describe the spin state of the two of those together is just to separately describe the spin state of each one individually. And we've been doing that with this notation here. My clicker seems to be malfunctioning. Let's try that again. There we go. One way to do that is by saying, we've picked a z direction in space, doesn't matter which direction it is, but we can then, we know that the electron and the proton are both spin 1/2 particles, and that means their little s quantum number is fixed for each one. So we would say S1 equals 1/2, S2 equals 1/2. There's nothing we can do to change that, but their SZ state, this first arrow indicates SZ of particle 1, maybe that's the proton, and this indicates the SZ state, either M sub S equals plus 1/2 for spin up or minus 1/2 for spin down. And those correspond to angular momentum Z components of plus or minus h bar over 2. So we can describe them separately, and there are 4 different states that the combined spin could be in. Again, we're ignoring the spatial wave function. This is one way to denote it. I'm writing it a different way that I didn't have in this slide yesterday, just because we're going to start denoting it this way in the table of Clebsch-Gordon coefficients, which is coming up very shortly. So, of course, so here I'm denoting it by M sub S of particle 1 and M sub S of particle 2. So this would be the up state, this would be the down state, and so on. It's equivalent to the other way of writing it. So we have a 4-dimensional vector space, and this is one way to write a basis. But just because you pick one basis doesn't mean that's the only possible basis, and not always the most useful one. The other possible basis describes not the individual angular momentum state of each particle, the spin 1/2 particle, but rather the combined angular momentum state. And we said there are, again, it's a 4-dimensional vector space. There have got to be 4 different vectors which can form the basis of this. And they correspond to total combined spin angular momentum. That means S squared eigenvalue corresponding to little s, either equals 1 or 0. And of course, for s equals 1, we have 3 different M sub S values, 1, 0, or minus 1. For that state. So there's 4 different possible states that the combined angular momentum can be in. Why might we be interested in describing this? Is okay, and I should say, when I write it this way, I'm not writing kind of the same thing as we are up here. It looks like a ket that has 2 numbers, but these 2 numbers mean M sub S of particle 1 and M sub S of particle 2. This way, when we're writing it, even though it looks kind of the same as the ones we have up there, it corresponds to the total S quantum number and the total combined M sub S quantum number. So it's hard to tell when you're just looking at the numbers what it means. Usually when I give these, I'll say, oh, where the numbers mean this or they mean this there. So you should know when you're looking at it. A lot of times we'll have, one way you might know the combined spin state is by saying that I know, suppose that a particle decays and I know its spin and I know its spin Z component before it decays, right? So maybe it's a spin 1 particle and its spin Z component quantum number is plus 1. And then it decays, and it decays to a state with 0 orbital angular momentum. Well, that means that the spin angular momentum before the decay has to equal the spin angular momentum after the decay, but after the decay, maybe we have 2 particles. And so we know that since angular momentum is conserved in that decay, the state described it as S and M sub S before the particles decays should be the same as the combined total angular momentum description after the decay. So that's how we might want to describe them this second way rather than the first way. And then if we want to find information about what the individual particle spins are, well, that's what we're about to talk about. Okay, so we worked really hard, or Griffiths worked really hard, and we did sort of a clever trick where we said, you know, I can write those combined spin states as a linear combination of the individual spin state description. We got a little bit lucky by, you know, noticing that we could add and subtract some things and then get some eigenvectors out of it. But in any case, we've got a relation between them. And the idea is this is just one example where we've got two spin 1/2 particles of a bigger and more general problem. In general, you might say, well, what if I've got two different particles and one of them has a certain spin quantum number and the other, you know, so maybe it's a spin 3/2 particle and particle 2 is a spin 1 particle. How can I write the combined descriptions as a linear combination of the individual descriptions? And the answer is, well, you probably don't want to try and get lucky like we did in the discussion that's based on what you read in an example in Griffiths. It's a pain and it would take a lot of creativity. And so since that sums and difference argument seems like it's not going to work out in general, we do it a good old-fashioned way. And what we do is write out in this basis, right? We said there's a 4-dimensional vector space. That means we got 4 basis elements. We're going to write out a 4x4 description of what S squared is and find its eigenvalues and eigenvectors, right? So we fill in the matrix elements the same way we've always done. So you got to kind of think about this, but there's a straightforward way to do it just using standard linear algebra techniques. Then we do the same thing and find the eigenvectors, 4-element eigenvectors, the same way. We're not going to do any of this, but I'm just telling you how you fill out the table of Clebsch-Gordon coefficients, okay? And then, you know, we can find out the combined spin states, how they are a linear combination of the individual spin states by the elements that come out in the eigenvectors. Okay. So let's just do some counting here. Suppose we've got two particles. Particle 1 has a spin quantum number S equals 2, and particle 2 has a spin quantum number S equals 3/2. Just by thinking of, you know, how the dimension of the vector space ended up being 4 when we had 2 spin 1/2 particles. Here we've got a spin 2 and a spin 3/2. What dimension vector space are we going to have if we combine a spin 2 particle and a spin 3/2 particle? So I've got so many people on Zoom, I better display you guys so I can see you holding up your votes. I've got to translate numbers into letters. Okay, okay, now Elvis is giving some sort of thing I can't read. Oh no, maybe it's a G. Okay, good. Let's see the vote of you guys in the classroom. The votes I'm seeing are G's, and the correct answer is G. It's hard to tell in the classroom, but it just turned red right there. So where does that G come from? Alvis, you want to explain how you got 20 there? We can't, you're muted.
Testing.
Yes, we got you now.
Well, spin 1 has a total of, no wait, or spin 1 is equal to 2, so it has a total of 5 possible states. Spin 2 has a total of 4 possible states for 3/2. And therefore you just multiply them together to get the correct dimensions.
Right. We you know, just like we said, if we have, for the spin 1/2 case, we had two states, spin up or spin down for particle 1 and 2 for particle 2. We multiply those together to get the total number of all possibilities we could get for particle 1, right? 2 possibilities for particle 1, 2 possibilities for particle 2 gives 4. And here Alvis is saying for spin 2, the Z component for particle 1 could be in the collection 2, 1, 0, -1, or -2. That's 5 for this one. And spin 3 halves could be 3 halves, the Z component of spin, quantum number, M sub S for particle 2. Could be 3 halves, 1 half, -1 half, or -3 halves, right? Going down by integers for the M sub S quantum number. So that's 4 for particle 2. And that means we have 5 choices for particle 1, 4 for particle 2, and so 20 choices for all of them, right? So the dimension of that space is 20. Now, if we think of it in terms of total spin angular momentum, that's thinking of it in terms of the individual spin states. Now, if we think of it in terms of the total, what values for the combined quantum number S, which goes into our S squared expression for the square of spin angular momentum? Well, it's going to range from, if you have particles of spin S1 and S2, it's going to range from the magnitude of S1 minus S2, right? But it's going to be a positive number for that, up to S1 plus S2 in integer steps. Okay, so that means, for example, in the spin 1 half case, it would range from 1 half minus 1 half, or combined spin 0, up to 1 half plus 1 half, which is spin 1. And that's what we found, right? We had the S equals 1 triplet and the S equals 0 singlet. Those were the only case we found. Okay, so here's a question. It's not really a voting question, but just something to discuss. Particle 1 has spin 1, particle 2 has spin 3 halves. What are the possible combined S values for the system, and how many states correspond to each S value? I have this as a capital S here. I usually capital S. Maybe I can't remember how I was thinking of it when I wrote this, but this would mean the magnitude of the spin angular momentum, right, with an H bar in it, as opposed to combined little s. So maybe it's simpler to ask, what are the combined little s values that are possible here? And then how many states correspond to each little s value? Let's go, since this isn't a voting question, let's go to the board. So I've got S1 equals 1 and S2 equals 3 halves. That's all that really matters here. S1 equals 1, S2 equals 3 halves. And if we're talking, it's hard to tell on here, but these are supposed to be little s's. So if I want the combined little s value, what are the options for little s? In other words, what range can it roam over? We just calculated for 1 half and 1 half. We ended up getting 0 or 1. What is it here? Yeah, we take the magnitude of the difference of these two. 3 halves minus 1 is 1 half. So we could have 1 half all the way up to the sum of these. This is 2 halves plus 3 halves is 5 halves. And we're going to go in integer steps. So 1 half, 3 halves, or 5 halves. And in fact, maybe I should leave room to write how many states we have there. Okay, the second question was, how many states correspond to each one of these? What's the number that goes along with the 1 half? Or what M sub S values are allowed? The combined M sub S value that corresponds to a combined spin quantum number of 1 half. M sub S equals minus 1 half or plus 1 half. So we've got 2 possible quantum numbers, right? Just going from minus s up to s in integer steps. 3 halves, M sub S equals minus 3/2, minus 1/2, or 3/2. So we've got 4 states corresponding to this. And 5/2, I'm betting I have 6 states, right? Minus 5/2, minus 3/2, minus 1/2, 1/2, 3/2, or 5/2. So the total number of states is 6 plus 4 is 10 plus 2 is 12 total states. Does that agree if we count them up the way we were doing before, where we were multiplying the numbers for these two? Well, let's see. How many possible states are there for particle 1? 3, right? Because it goes from -1 up to 1 in integer steps. So -1, 0, or 1. So we have 3 possibilities for particle 1, z spin angular momentum. And then for 3/2, we've got 4. And if we multiply 3 times 4, we get 12. So it all adds up. It's just a different way of expressing the basis using one combination or the other. Any more questions, including you Zoom folks, on that counting? I think maybe I had one more counting example here. Let's see. If particle, is this the one we were, no. Spin 1 and spin 3/2, how many linearly independent spin states can they find? Yeah, so we just did this, 12. That's what we just calculated. Here's the one we did before. This is just another counting example. Spin 1 equals 2, spin 2 equals 3/2. We said this one has 5 states, right, associated with it. This one has 4 states, so we counted the product of those as 20. If we count it the other way, we would say, well, let's see. 2 is the same thing as 4/2. 4/2 minus 3/2 is 1/2. So we would have to go from 1/2 up to 4/2 plus 3/2, which is 7/2. So I've got to go from 7/2 down to 1/2, count up the number of states associated with each one. You can do that, but it's 8 plus 6 plus 4 plus 2, which is 20. So it adds up either way we do it. Okay, that's just counting the number of states. Now the question is, well, just the same way we had those sums and differences of the up, down, and down, up. In general, if I've got a spin 1 particle is particle 1, spin 1, and particle 2 is spin 5/2 or something like that, then how do I write a particular combined description as a linear combination of the individual descriptions? And so there's sort of a complicated, it's just a coefficient, right? We have to say the combined one is some linear combination of all the individual ones, and those coefficients are called the Clebsch-Gordon coefficients. And they have this somewhat complicated symbol, right? It has all the things you could want in terms of it, right? C, S1, S2, S, M1, M2, and M, where M is the combined quantum number. And we have to sum over all cases where, if you have SZ equals, the combined SZ equals 3, then we know that the individual SZs have to add up to the combined SZ quantum number. So there's some constraints. We can't just sum over everything, or at least the other ones would have 0 coefficients. Okay, one way to get those Clebsch-Gordon coefficients, or to see how to do them, is to say, well, let me first write S sub m equals S sub m. That's kind of a trivial identity. Forget about this stuff out in front here. I'm going to write S sub m equals S sub m. And what I've written out in front here, the sum over all of these states such that M1 plus M2 equals M, is one way of writing the resolution of the identity. So this thing out in front here is the identity operator. I'm just writing it as 1 there. So this is saying, tell me how to expand S sub m as a linear combination of the SM in terms of M1 and M2. And the answer is the coefficients are these things over here. These are numbers, right? Each inner product is a different number. And so those coefficients that we're seeing over there are the Clebsch-Gordon coefficients. So that tells you, you know, if you want, that's how to compute those Clebsch-Gordon coefficients. Here's the table that you see in Griffiths, and we want to make sure we know beyond a shadow of a doubt how to use this table and read it. It's a great table. Particle physicists use this all the time to help out with decays and interactions where angular momentum is conserved. It can be used to combine both spin and orbital angular momentum as well. But here we're just thinking of it as spin. And so the idea is it's got different sectors in it. The different sectors correspond to the kinds of particles you're combining. So here we're saying, I've got a spin 1/2 particle and a spin 1/2 particle. Okay. And it tells me, right? So we said when we have a spin 1/2 particle and a spin 1/2 particle, and I have the state, you know, the combined spin state, combined S equals 1, combined M sub S equals 0. That's equal to some linear combination in the table of the individual states. So these things shown horizontally in all these parts of the table are individual Z quantum numbers, right? So this would correspond to M sub S of particle 1 of 1/2 and M sub S of particle 2 of, boy, it's hard to read that. Is that a minus 1/2 there? I'll have to look on the actual table. I need to make a more high quality scan of this, but if you have your book, you can look in there. Yes, it's a 1/2 and a minus 1/2. We know that from our work, right? So this is saying 1, 0 is some linear combination of spin up, spin down, and spin down, spin up. You can't really see them, at least here in the class. It's a little bit too blurry. What are the coefficients? Well, the coefficients have to do with these numbers here. And Griffiths tells us, well, in order to make the table as small as possible, the numbers always have a square root over them. So if I see a 1/2 here, the relevant coefficient is 1/√2 or root 1/2. And you'll see that some of the coefficients have minus signs in front of them. And he says the minus sign, if present, goes outside the radical. So that means if you see a minus 1/3, like I'm seeing there, that the coefficient is minus root 1/3 in that case. So looking at this table up here, I don't know, yeah, just looking at that table and sort of examining the 1, 0 state, I'm going to write down what it is on the board, but I'm going to leave it up for you guys who are looking at it, and then we'll switch to the board in just a second. That table, and in fact, for those in the classroom, I printed out Clebsch-Gordon tables because I wasn't sure if you have your book. This is the same one that's in the book. And it's still a little blurry, but at least it's more legible than the one that's on the slide. If you're at home, you'll have to Google it or look in your textbook to find a clearer version of the Clebsch-Gordon coefficients. So I'm looking at this particular 1, 0 here. So that's combined S equals 1, combined M sub S equals 0. So I'm going to write that down. And it tells me how to write it as a linear combination of spin up and spin down in a way that we've already seen. It's saying that, well, maybe what I can do is stop this. It's telling me that I'm writing now S, M sub S, those combined states like this, that, uh-oh, did I not pin the video here? No, I did. It's telling me that this is equal to, so 1, 0 is equal to root 1/2, you always got to remember that square root of, and the first one is plus 1/2 minus 1/2. Plus root 1/2 minus 1/2 plus 1/2. Okay, so those coefficients are coming from the table. in this position, oops, this position and this position. I'm looking at those, I'm putting roots over them. There are no minus signs to worry about. It's also telling me that the 0, 0 state, that's combined S equals 0, combined M sub S equals 0, is equal to root 1/2 times the 1/2 minus 1/2 state minus root 1/2, because there's a minus sign. So I'm looking at this second column here. Kind of hard for me to point so everyone can see, but I'm looking at this. The 0, 0 state is root 1/2 times this state minus root 1/2 times this state. Minus root 1/2 times minus 1/2 plus 1/2. Okay. And those are the results we found out before. It's also telling me that the, for example, combined S equals 1, combined M sub S equals plus 1 is just equal to the plus 1/2 plus 1/2 individual particle description state. We found that before. So what we're seeing there on the board right now is an expression we showed before. If I back up here, whoops, few slides. It's an expression of what I had written on the board is this second line and this fourth line, right? This is S and M sub S combined. Now we're writing it as 1/2 minus 1/2 instead of arrow up and arrow down, but means the same thing. Coefficients in this case would be from the table. Okay, let's go do a different one.
Doctor?
Yeah.
I think your microphone is cutting out.
Oh,
We missed like the last 3 sentences that you said.
Yeah.
right again. Can you guys hear me now?
Yeah.
Yes.
Okay. Maybe
Um,
maybe I knocked my USB thing. I'm not sure.
Yeah,
Let-
and I also have a question.
Yeah.
Did you flip because I thought like the first one on the board is 0, 0, and the second one is 1, 0.
Well, so you're saying based on the table of coefficients, you think that, or based on the slide I just flashed up?
I mean, based on the board that you write.
Yeah, okay, but you're saying I have them incorrectly written compared to the table when we read the table?
Yeah, maybe because the first one I thought is 0, 0, and the second one is 1, 0, I think.
Well, so when I look at 1, 0, right here, can you see where I'm pointing right now? The
Mhm.
1, 0 column there. Notice that neither one of these has a minus sign in front of it. So that
Okay.
means 1, 0 is this coefficient times this individual description state. So that's up, down.
Mhm.
1, 0 is root 1/2 times this plus root 1/2 times this. So there's a plus sign there, right? So for the 1, 0 state, I have a plus sign between them. And for the 0, 0 state, there's a minus sign between them. Going back there again, tell me if I'm not addressing your issue. For the 0, 0 state, it's hard to see here, but if you look carefully at the screen, there's a minus sign right there.
Okay.
And so I have root 1/2 times this state, and then minus root 1/2 times this state. Is that clarify the confusion, or is that, do you want to ask them another question, Yichen?
That's okay.
Okay,
Yeah, I
let's-
think it works.
let's do another example. Okay, so looking at that, let's look at this particular table down here. Now, so this is for combining a spin 3/2 particle and a spin 1 particle, right? You always look in each region of the Clebsch-Gordon coefficients, it tells you what kinds of spin particles are being defined. And because the 3/2 comes first, that means in the individual particle descriptions for their spin states, this spin state, the first one to appear, corresponds to the 3/2, and this one corresponds to the spin 1 particle. It didn't matter up here, everything was symmetric. So you could, if I were doing an electron and a proton, doesn't matter which one I consider to be first and second, as long as I keep it straight which one I'm using. Okay, it's kind of hard to see these coefficients here, but I can also, I guess I should also mention, you can read these horizontally. So not only does it tell me the combined spin state as a function of the individual spin descriptions, but I can read an individual spin description as a function of the combined spin state. So looking at this case, I would say, so I've got a spin 3/2 particle and a spin 1 particle. The state where the spin 3/2 particle has an m sub s of 1/2, and the spin 1 particle has an m sub s of 0, that's equal to √3/5 times combined s 5/2 combined m sub s minus 1/2 plus √1/15 times combined s 3/2 and combined m sub s minus 1/2. And I think that's a minus sign there. Yes, there is a minus sign in front of this 1/3. It didn't come out very well in my slide. Minus √1/3 times combined spin 1/2 combined m sub s of plus 1/2. So yes, combined m sub s of plus 1/2. It's really hard to tell. Even my printed out version is not very good. I better flip to the page in Griffiths where he has this table. I stole the one that I'm looking at off the web, and it's just not, it's a scan from Griffiths. It's just not a good enough scan. I'll have to do my own higher quality scan. Table in Griffiths is pretty microscopic too. But yes, all three of these, it's hard to tell here, but this sign, and this sign, those are supposed to all be pluses. I was thinking those two were minuses, but they're pluses. Okay, so if I write that up on the board, I know I'm going to take it away from those of you who are on Zoom, but writing out how to write out that line in there, it's going to tell me that so if I'm doing a spin 3/2 and a spin 1 particle, it's telling me that the combined spin state of plus 1/2 0 okay, and since I'm reading a row here, this is the m sub s of particle 1, and this is m sub s of particle 2. So that's an individual description there. I know it's hard to see, right? I mean, if you just write this, it would seem at least a little bit ambiguous. How do I write that as a linear combination of combined spin states? Well, the coefficients are √3/5 times the combined spin state that's sitting up above it is 5/2 1/2. Okay, so here, again, just to clarify, this means combined S and combined M sub S. If I don't write that above, it's a little bit confusing, or more than a little bit confusing. Plus √1/15 times 3/2 1/2 plus, again, minus in this case, minus √1/3 of 1/2 plus 1/2. Okay, again, that's an S M sub S state that's being written there. Any questions on this one, which was the row that I had, highlighted in red in the table there? If you got Griffiths, open it up to if you're at home, open it up to the Clebsch-Gordon coefficients table so that you make sure you can look at it while we're writing this stuff on the board. Right, so that's telling me how to do an individual spin state as a linear combination of combined spin states, which are up here. How am I going to remember that the horizontal ones are individual spin descriptions? Because look, the title of the subsection shows the individual particle spin. So that means, horizontally, the first one is 3/2 and the second one is spin 1. So these are individual particle spins. That's how I remember that. Whereas the ones perpendicular to it are combined spin descriptions. So for example, this is saying for a spin 2 and a spin 1 particle, it goes from 2 - 1 up to 2 + 1, or spin 3. So we could have a combined spin of 3. And we might say, well, what if the combined spin is 3 and the combined m sub s quantum number is 0? Well, apparently that's √1/5 times, I can't see on here. It looks like +1 - 1. I'll have to look in my table. I didn't mean to cover that up. +1 - 1, right? So that's spin 2 has an m sub s of +1, and the spin 1 particle has an m sub s of -1. And similarly, √3/5, 0, 0, and √1/5 -1 + 1 of the individual spin description states. Okay, we'll do an example in just a second. Well, okay, those are the examples. It's telling me to do worksheet problem 4. So this is the worksheet we were working on yesterday. I can't remember anymore if it was posted under yesterday's date for those of you on Zoom, or it's posted under the day before, Wednesday. But we're looking at problem number 4, which says, consider a spin 2 particle and a spin 1/2 particle together. What possibilities are there for the total angular momentum of the pair? And here I'm not asking for total angular momentum quantum numbers, but I'm asking for total angular momentum full stop. And that means you ought to write it in terms of h bar, right? When I say angular momentum, that means give me something with the units, and h bar has the units in it. If I say spin, that always means the spin quantum number, But if I say spin angular momentum, that means give me something with units of angular momentum along with it. And that's the √s times s + 1 times h bar. All right, so try problem 4 using the Clebsch-Gordon coefficients. I'll leave the table up here in case you just don't have access to one, even though it's a little bit blurry. The one I handed out on paper in class is a little bit clearer. Still a tiny bit blurry, but seems readable. you had a chance to do it, Riley, looks like it. Okay, let's discuss together. So we're combining, in the kind of notation that's in the Clebsch-Gordon coefficients table, we're combining a spin 2 and a spin 1/2 particle. And even if we had written them the other order, it doesn't matter. We're going to look in the 2 cross 1/2 section of the table, but we don't need that for part A. Part A just says when you combine those two, what possibilities are there for total spin? I should have said spin angular momentum of the pair. And the answer is you go from the sum of these quantum numbers to the difference, or difference, magnitude of the difference to the sum of those quantum numbers. So we've got 4/2, that's 2, minus 1/2, so that's 3/2, up to 4/2 plus 1/2, and that's 5/2 in integer steps. So we only get one integer step. So those are the only two possibilities for the quantum numbers of the total spin angular momentum. That's the spin, combined spin, if we were to say it this way. I asked for angular momentum, so we want to give something with units. So this means that the answers I should give for the two possibilities for angular momentum are root 3/2 times 3/2 plus 1 times h bar, right? The square root of the squared expression, and root 5/2 times 5/2 plus 1 all times h bar. Because I asked for angular momentum. So this is really, you could simplify what's under the radical, but that's the correct answer there. Any questions on A? Then in B, we're told, so one of the possibilities we found was combined spin of 3/2. So here's a state, combined spin of 3/2, combined spin Z quantum number of minus 1/2. That's certainly a possibility because 3/2 was one of our S quantum numbers that we are allowed to have. And this is certainly allowed Z quantum number there. I've got to write that as a linear combination of the individual particle description states. And so let me just flash on the Clebsch-Gordon coefficients. I'm looking, again, we're combining a spin 2 and a spin 1/2 particle. Even if I had said a spin 1/2 and a spin 2, this is the only relevant region of the Clebsch-Gordon coefficients because they're written in this order. That means for the individual descriptions, the first number corresponds to m sub s for the spin 2, and the second one corresponds to m sub s of spin 1/2. And our state was combined s of 3/2 and m sub s of minus 1/2. So I look up here along the top for 3/2 minus 1/2, and I'm seeing right here, there's 3/2 minus 1/2, and it's going to be a linear combination of these two individual spin description states. The coefficients are root 2/5 and minus root 3/5. I'm just looking at those, okay? And now I'm going to go to the board and we'll maybe flash back on here for those of you on Zoom. So again, looking down that column, my coefficients for 3/2 minus 1/2 are root 2/5 and minus root 3/5. And the individual states that are next to those, if I read to the left from those coefficients, I've lost my place here. We have a 0 minus 1/2. And also a, let's see, minus 1 plus 1/2. Okay, and when I'm doing this, these were read from the horizontal part of the table because we're in something labeled as 2 cross 1/2. That means this is m sub s of the spin 2. And this is m sub s of the spin 1/2. Same thing over there. So that's how to write it as a linear combination of those two states. There's just so much confusing notation. Griffiths also, I think, when at some point when this was originally, notice I'm only giving the individual m sub s's here. A long time ago, just like we're doing over here, sometimes we give individual kets with s and m sub s. And so sometimes people might write this state as a product of two individual kets and say, well, let's see, this one corresponds to the spin 2 state. So I'm going to put the s and then the corresponding m sub s there. And this one corresponds to the spin 1/2 state. So this is the s and this is the m sub s, also 1/2. That's a different, I know it's confusing, different notation for the same thing there. This is just a little shorter. As long as you know the context, then you know what the m sub s's correspond to, because they're corresponding to particles that have immutable spins, at least in non-relativistic quantum mechanics. Okay, any questions on that example? There's some in the homework that you'll see that I will post shortly and will be due probably Wednesday. Exams on Thursday. Here's one final question showing the kind of thing you can do or how you can use this in decays. So imagine that in some elementary particle decay, a W plus and a Z boson, both of those have spin 1, are emitted. So some particle decays into a W plus and a Z. They're both spin 1 particles. And somehow we know that the combined spin state is s equals 2 and m equals 0, m sub s equals 0. If we measure the Z component of the spin angular momentum of the W boson, what's the probability we get minus h bar? See if you can just read that off the table, sort of translating those sentences in and then knowing what to look for in the table. Oh, I'm sorry, and I see I forgot to share my screen. We're looking at, here's the question. Sorry about those of you on Zoom. The question is up here at the top. You heard it, but now you can see it in words. If we have, so we're concerned with the final state, and there are two particles there. They're both spin 1. Yichen, can you tell me what region, so if we've got two spin 1 particles, what region of the Clebsch-Gordon coefficients table are we going to look in?
So it's both spin 1, so I guess it's 1 by 1, which is like
That's
there.
this lower part. Yeah.
Yeah, because I cannot point it, so.
Yeah, I just meant left, right, up, down kind of thing. Good. And then, so since we're told, I'm not telling you how we got this information, but sometimes you know a lot about the state before, not just the spins, but you might know also the orbital angular momentum state. Suppose we somehow know that the combined state, spin state afterwards has combined s quantum number 2 and combined m quantum number 0. Within that subsection there, Alvis, where would I be looking in the table? I guess there are 5 bold outlined sections as I'm going down. Which one of those, if I go 1, 2, 3, 4, 5, which region are we looking in to answer that question, or to concern ourselves with the combined state s equals 2, m equals 0?
S equals 2, and I'm thinking the middle one.
Yeah, I agree, because the combined states are shown vertically here. There's S equals 2, M equals 0. So we're looking in this column here, and it's telling me how to write that as a linear combination of individual states. We want to know the probability that we get a W plus having a Z component of spin angular momentum of -1 h bar. How do I know whether I should be looking at the first, second, or third coefficient there? Well, it's a little bit confusing because they're both spin 1. And so, you know, if one was spin 2 and one was spin 1/2, I'd know which one corresponded to the first and second position. Here, the claim is it doesn't matter. I could just say, well, let's call the first one the W plus 1 and the second one Z. You'll see the answers are the same if you reverse that assumption. And so if we're saying the first position in these combined states here, the leftmost position corresponds to the W, and we want the W spin Z component of spin angular momentum to be minus h bar. That's a -1 in that position, in the first position. My table again on the slides is a little bit blurry, but if I look at the actual table there, that is the third of the 3 possibilities. So I'm looking down over here at this one. That's for saying the first one is the W and the second one is the Z, then here's W equals the W spin Z is -1 quantum number, and the Z's spin Z is +1 quantum number. So that would correspond to a minus h bar of Z spin angular momentum. The coefficient is plus √1/6. Therefore, the probability is the square of that, which is just 1/6, which shows you another great thing about the table is that because they've left the square roots off, everything has a square root over it in these coefficients. What you're seeing here, as long as you ignore any minus signs, are probabilities. So the probability is 1/6 that we get a minus. It's 4/6 that we get 0 for the W's Z spin angular momentum, and it's 1/6 that we get +1. So they add up to 1. So what we're seeing in the table is really some probabilities since they've left out the square roots. Okay, so looking there, the other possible outcome possibilities are plus h bar, 0 h bar, or minus h bar. And the probabilities are 1/6, 2/3, and 1/6 respectively. So it's a sort of a great table in that there's a whole lot of information packed into a, once you get used to it, a very easy to read kind of format that doesn't take up much space. So people use it in particle physics all the time. Any questions on that? I think that's the last thing I wanted to talk about today. And since we're almost at the end, I'm just going to call it quits here because that's the end of section 4. Section 4.4. Any questions on that?